Hi, everybody. My name is Julie Bloomquist, and I'm one of the co-chairs of the St. Louis SQL Server and Business Intelligence Group user groups. Gary Polinsky is also on. He's the other co-chair. And today we are very fortunate to have Sanil Mhatre joining us for Modeling Made Easy. Sanil used to live in the St. Louis area, and then he went and I guess immigrated to Canada, and he's out of Vancouver. So we're very pleased that he's joining us virtually. Oops. There we go. The next meeting for July is going to be an evening meeting. Is going to be Kathy Kellenberger. Hold on. And she's going to be talking about what's new in SQL Server 2022. Data Saturdays and SQL Saturdays are back in full swing. You'll be able to see what's coming up on the schedule here. And you could also go to the datasaturdays.com or SQLsaturdays.com. The Past Community Summit is beginning on November 15th, goes through the 18th, and there are some pre-conferences. They do have a hybrid conference in Seattle. This is the second year this is taken over. Well, this has been taken over by Redgate, the Past Data Summit. So when I registered, it was $395 for the virtual, and you do have access to the recordings, and you do have real-time access to the lectures. And then they also have in person. There was a price increase. I think it's $495 now. But it's a great opportunity, this summit, for sharing information and seeing some great lectures. And then here today, this is all about Sanil, what we're going to be covering, and his background. We really appreciate him joining in the morning to be at our lunchtime. And Sanil, I'm going to pass the presentation over to you.
Thank you, Julie. I think my camera stopped working, so let's try it again. Why no why?
Okay. And you're not sharing, and you sound a little soft. You guys, all questions, if you want, you can put them in the chat. And
hello, is this better?
Yeah, that's great. I can see you. You should be able to share your screen.
Yeah.
And then if you have questions, just type them in the chat, and when there's a stopping point, we'll read the questions. So I'm seeing, there we go.
All right, can everyone see my slide deck now?
Yes.
Perfect. Sorry about that. I think some cable went loose either on my side or somewhere in the clouds, and the webcam disconnected for a second. All right, so today we are going to talk about topic modeling. It's a deep dive in the field of text analytics, or what's commonly known as natural language processing. I'm Sanil Mhatre. I am the lead data scientist at Worldwide Technology. They're headquartered in St. Louis, Missouri. As Julie mentioned earlier, I used to live in the St. Louis area for about 10 years before I moved to British Columbia, Canada. And a quick fun fact about me is now I live on an island, literally speaking. So I'm a data scientist with extensive background in data engineering, business intelligence, database administration, and enterprise data platform architecture. I have worked with Azure, AWS, Google Cloud Platforms, um, SQL Server, the O word, Oracle, that no one in the SQL world likes to talk about, Snowflake, Postgres, and MongoDB. And some of the non-technical things that I like to work on is Agile. Um, I have been an Agile coach for several years, and I currently am an Agile coach as well as the lead developer on my team. I love doing mentoring for STEM students, for folks who are brand new to the technology industry, as well as college students who might be interested in learning more about technology and our workplace. Um, I love speaking at user groups and conferences. I like to blog. I mostly blog at Redgate, and I like to volunteer whenever there are opportunities to volunteer in person, which are far and few in between these days. You can find me on Twitter at SQL Superguru, and you can find me on LinkedIn as well. And as I mentioned, I have written several articles. Most of them are on Redgate Simple Talk, and it's pretty easy to find me. My name is pretty unique, so if you just Google for my name, easy to find me. All right, so let's jump into what are we going to talk about today. So the agenda for today is we are going to discuss briefly what is topic modeling. We are going to look into how can you prepare your data in such a way that it suits the exercise of topic modeling. We are going to talk about how to train a model and evaluate the outcomes from a model. And finally, this is the most fun part, we are going to look at the output of the model and figure out how do you interpret human readable topics from the output of a machine learning model. So let's jump right into it. At a very high level, uh, what is natural language processing? So natural language processing is a machine learning process that helps figure out human language text data using software. There are different types of natural language processing that one could do. Sentiment analysis is one of them. My previous talk, Sentiment Analysis Made Easy, is all about how can you perform sentiment analysis on text data. The next thing you can do in the field of natural language processing is named entity recognition. It's an area where you can identify the name of a city, maybe the name of a country, the name of a technology, or any proper nouns. Any named entities can be identified from a body of text. They could potentially be classified as well. If, say, the text is something like, I went to Seattle for the past summit last year. Uh, a named entity recognition algorithm should be able to pick out the name of the city, Seattle, and correctly classify it as the name of a city. Then we have text summarization. It's the art of using machine learning to identify the main topic, the main theme of a large body of text. It can be pretty helpful in summarizing a large document, maybe summarizing a story, a novel, a book, something like that. Next one is aspect mining. Uh, it talks about intent. And then the last one, the reason it's highlighted is topic modeling. And the reason it's highlighted is because that's what we are going to deep dive into today. Let's drill down into topic modeling. A topic modeling is an unsupervised machine learning technique. What we mean by unsupervised is there are two broad families of machine learning techniques. Uh, the more commonly used is supervised, where you show a machine learning model 10,000 pictures of cats. And every time you tell the machine learning model, this is the picture of a cat, this is another picture of a cat, this is the third picture of a cat, so on and so forth. And you teach the machine learning model to identify the fact that it's a cat. And hopefully, after looking at 10,000 pictures of a cat, you show the machine learning model a picture of some animal and it will be able to detect if it's a cat or not. That's supervised machine learning. You're teaching the machine learning model how to go about doing its job. The unsupervised machine learning technique is where you don't have any training data. You have a picture of something and you can't really tell the machine learning model this is the picture of a cat because you yourself don't know what is this a picture of. You're using the help of the machine learning model to figure out yourself what is this a picture of. So topic modeling falls under that category of unsupervised machine learning technique where you really don't know what you're looking for and you're using the help of the machine learning model to explore and figure it out. Typical topic modeling algorithms will represent your text document as a collection of topics. These models then find the relationship amongst the various data points, the various topics that it has collected in the text document, and then it applies a technique called latent dialect allocation, which is a probabilistic modeling technique to come up with the top 5, top 10, or top n number of topics that you can find in a text document. So an LDA model will think of a text document as a distribution of topics, and then it will think of a topic as a collection of words. I'll take a brief pause here before jumping into the latent dialect allocation model and how it works to talk about what is the real life application of this seemingly magical technique called topic modeling. So let's say you have a database of call center transcripts where people are complaining or where people are calling in to complain about something or to seek help with something. And all you have is the transcripts of those calls. You don't really have any metadata about what was the reason this customer called for. Someone has just dumped all these call transcripts at your desk and asked you to figure out what are the top 5 things that people have been complaining about the most. That's where techniques like topic modeling really shine, where you can run all of the text transcripts through a topic modeling algorithm and have a reasonable confidence that this topic modeling algorithm will be able to identify the top 5 things that the customers are complaining about when they're calling up your call center. I hope that helps with putting into context some of the real life applications of this machine learning technique before I jump into the technique itself. I'll take a brief pause if there are any questions about the things we discussed so far.
If you have any questions, just type them in the chat. I do not see any questions at this time.
Sounds good. Thank you for keeping an eye out for that, Julie. And my audio is still good, right?
Yes, it is.
Perfect. All right, let's go on to the next slide. So this slide gives a very, very high level pictorial understanding or a pictorial overview of what exactly is a latent dialect allocation algorithm. On the left hand side, you start with a collection of documents. What a document really is simply a text file or multiple text files. In the example that we talked about previously about call center transcripts, uh, transcript of each and every call can be thought of as a document. So when you are analyzing transcripts of 10,000 calls, you have 1,000 documents. That becomes the collection of documents that you would feed into the latent dialect allocation algorithm. Uh, I'm going to now refer to it with its abbreviation LDA because the full name is quite a mouthful. Okay, so the LDA algorithm does its magic. Uh, it implements a few techniques that we are going to deep dive into. But once it has done its magic, it will figure out that the collection of documents is basically a collation of topics. The document has 10, 5, whatever number of topics, and these topics have a certain distribution across the various documents. So each document is a collection of topics. Now, what exactly is a topic? A topic would become a collection of words, or I should say it the other way around. A collection of words becomes a topic. All of this would be would become clearer as we walk through the algorithm. At this point, uh, what I want you to take away from the slide is that the LDA algorithm, the way it works is it's going to identify a number of topics in the document, and it's going to tell you what is the distribution of those topics across these documents, and then it's going to also tell you the cluster of words, the collection of words that represents each and every topic. All right, so why do we use topic modeling? We briefly talked about this a few minutes ago, but you need topic modeling when you are looking for meaningful and actionable insights. So in the example that we talked about, from all of your call center transcripts, if you're looking for top 5 problems that people are calling about, so that maybe you can take those problems and try to address them instead of depending on your call center uh, to address those problems. Maybe you want to address those problems in your software, in your application, or maybe in your business process. So it helps you to identify actionable insights. There are some limitations of the other techniques we talked about, namely text summarization, aspect mining, keyword, key phrase, and frequency techniques. Most of these limitations can be overcome when you use topic modeling. While it sounds like magic and potentially sounds a little complex, uh, when this session ends, trust me, you will find that topic modeling is relatively easy. It's pretty robust and reliable, and those are some of the reasons why it is a very, very popular technique as well. So it helps you discover valuable business insights. And a couple of examples of these valuable business insights would be top 5 customer complaints, as we talked about before, or maybe top 3 suggestions for improvements from a survey. A survey example is what we are going to walk through as a demo, end to end, over the next few minutes. All right, so we talked about what is topic modeling. We also talked about why do you want to use topic modeling, what are the benefits of topic modeling. Now let's briefly talk about the process itself. of topic modeling. It's important to briefly go over the process at this time because this flowchart is what will be implemented in code over the next few slides and over the course of our demo. So the very first step is you acquire your data, you import your data into a Python data frame, and then you go about cleaning your data. So you perform some basic cleaning processes like removing numbers, removing punctuations, removing special characters, all of that fun stuff. Then you tokenize that data. What you mean by tokenization is machine learning models typically like to work with numbers. They are mathematical and statistical models. They like to work with numbers. So the process of tokenization converts the words, the individual words in your dataset into IDs, numerical IDs, or tokens. Then you perform some steps called elimination of stop words. Stop words are basically the most commonly used words in the language that have very little meaning. So words like a and the prepositions, all of those filler words that we typically end up using, all of those are called stop words. They have very little meaning, and it's good to eliminate those when you're feeding the data into your machine learning model. So that's stop word elimination. Then you identify n-grams. By n-grams, we mean bigrams, trigrams, or um, higher level, which is a collection of two words, a bigram. A collection of three words together is a trigram. And as you go into higher levels, they become 4 grams, 5 grams, and whatever. So something like a word like not good, or sorry, two words, not and good. When you look at them individually, they mean something different than when you put those two words together. So those are the kind of things that you want to look at as a bigram rather than looking at those two words individually. In similar ways, there might be trigrams that are important to look at because those three words, when looked at separately, mean something completely different than when those three words are put together. Then we come to lemmatization. And this is a technique in natural language processing where you lemmatize the word. So what it means is you reduce the word to its common form. And we'll look at examples of lemmatization as we go through the demo. Once you're done with all of this pre-processing, then you create a dictionary of your processed data. And from the dictionary, you build a term document frequency corpus. So how many times has a particular word or a collection of words occurred in a particular document? You are building that corpus, which is basically a body of text. Corpus is Latin for body. All right. So that covers all the pre-processing steps. Then you go about building your model. It's an iterative step. Trust me when I say this, building the model is actually the easiest step. It's literally 4 lines of code. And you build the model, and then you look at the model performance metrics. You look at an output called the intertopic distance map, and you interpret if that output makes sense or not. Is that output appropriate or not? And if it's not appropriate, then you run several iterations of retraining the model until that output looks appropriate. What should an appropriate output look like? We are going to jump into that during the demo section. But once you have found the appropriate iteration, then you finalize the model, and then comes the part where human intelligence comes into picture. No artificial intelligence so far can do this. You need a human to look at all of the output of the machine learning model and then label the topics. And this will become clear as we jump into the demo. So the next slide is going to be about the demo. And as we jump into the demo, or before we jump into the demo, I'll take a quick pause if there are any questions about the material we covered so far.
Hey, Sanil, Timothy Liu asked if this was an example of clustering. I think when you were talking about the words.
This is not necessarily an example of clustering. That's a clustering technique that is commonly used in machine learning, k-means clustering. It is a derivation of that technique because you can't apply the standard clustering techniques to text data. But the latent dialect allocation algorithm, Timothy, you're right, it is built on top of the typical clustering technique.
And he's got a follow-up question of, is there a means of obtaining sentiment analysis through LDA, or would that be a completely separate model?
That's a great question. And as far as I know, LDA will not help you with sentiment analysis. Sentiment analysis is the typical technique where you would try to identify the degree of positivity or the degree of negativity in your text and maybe try to assign a numerical score to the strength of the positivity or the strength of the negativity. It's a completely different technique, completely different algorithm. And as far as I know, the LDA package, which is part of GenSim, doesn't have that functionality built in.
And that's it for questions.
All right. Thanks, Julie. So let's look into what are demo use cases. So for folks who may have joined my previous presentation about sentiment analysis, the demo will look very, very similar, or the demo data will look very, very similar. I'm using the exact same data set for this demo as well. It's a quarterly team health survey. This is real data from my company. My organization every quarter runs a team health survey for all teams within the IT department, where they simply ask every team to answer one open ended question. How do you feel about your team's health in this quarter? That's it, nothing else. The text that we gather in the past, the managers of every team were required to manually read through all of the text responses and make their own interpretations. Since I started working on sentiment analysis and topic modeling, uh, I took over using machine learning to help our managers analyze this data in a much more standardized and robust way. So we have 9 teams as a part of this demo data set. Those 9 teams report up to 3 managers, and we have 4 quarters worth of data. All of this comes from a total of 300 responses, and the raw data is in an Excel file. I have de-identified the data, removed any proprietary information from the dataset, but this truly is the real survey feedback data from my organization, not made up data at all. Okay, so the demo environment. We are using Anaconda, and I'm launching a Jupyter notebook with Python in Anaconda. Anaconda installation is pretty straightforward. You can simply search for Anaconda online, and it's free to download and use as a personal edition. If you want it as an enterprise edition, which comes with all the support that enterprise editions typically come with, it will cost you money. But the free edition, the personal edition, is free to use. I'm going to use a package called Spacey. It's really good to deal with the process of lemmatization. I'm going to use NLTK for stopwords. GenSim will be used for topic modeling, and PyLDAVis is a package that will be used for interactive web-based visualization for the outputs of the topic modeling algorithm. And then there are typical pandas libraries and packages that you use in most of your machine learning workloads. It's pandas, NumPy, matplotlib, and word cloud over here. Um, uh, I'm using the word cloud to kind of compare and contrast how and where does topic modeling really shine compared to the word cloud. Okay, I'm going to switch over to my Anaconda screen. All right. So this is the Anaconda navigator. When you launch Anaconda, this is the typical home screen. On this home screen, you would launch this Jupyter notebook. So simply click on the launch button. I'm not going to do that right now because I have already done these steps and I have a Jupyter notebook open over here. So this is what a Jupyter notebook setup looks like. All right, there are cells where you can write code. There's this little run button to execute the code, and then the output of your code, if any, will show up down here. Very, very straightforward, very interactive. I love using Jupyter notebooks. Okay, so let's switch back to the slide deck because I do want to talk about. Oh, no, not the slide deck. We are actually in the demo. All right, exciting time, Jupyter notebook. Okay, so the very first cell is where I am installing the GenSim package. I don't want to install the latest package because it removes the support for some of the wrappers that makes my coding significantly easier. So I'm installing this particular version. If you are following this demo, I would highly recommend that you install this specific version of GenSim. Then I'm importing a bunch of other libraries and packages that are going to be useful. I wouldn't worry about running through this code with you at this time. After the session, I will share a link to the GitHub repo where this Jupyter notebook is at, and all of this code will be available to you for use. Okay, so the next set of code is where I am importing my Excel file into this Jupyter notebook. So simply using pandas read Excel method and pass in the location of your Excel file. I'm only interested in the response column of the Excel file. So I am going to create a new data frame that simply has that one column, the response column. I don't need any other columns at this time. I'm doing some pre-processing steps of converting that into string, and then I'm converting it into lowercase. And finally, I am eliminating everything that is not an alphabet. So I only want A through Z. I don't want anything else. No numbers, no special characters, no punctuation, right? And finally, after all of this is done, we are going to take a look at what does the data frame look like. So let's run these steps real quick. Shouldn't take long. Oh, and it's already done. So the first print statement gives you an impression of what the Excel file looked like. It has columns called period, which has the quarter name. So 2019 Q1 in the case of this first row, manager name, team name, and the text response. A part of the text response that you can see here is we are a fun team that works well together, so on and so forth. And then you go through all of these initial cleanup steps and you print the brand new data frame that resulted from all of this cleaning. And now we have the text over here. We are a fun team that works well together. So it removed the punctuations. It took care of uppercase, lowercase, things like that. Good so far?
Yes, looks good.
Okay, so the next thing we are going to do is from this text data, we're going to create a word cloud. For folks who have created word cloud in the past, you might know or you might have experienced that how much managers or leaders love word clouds. Um, but for folks who actually make use of some of these analysis, they will tell you that a word cloud doesn't really offer a lot of rich information, which you can see over here. What you learn from this word cloud is that the most frequently occurring word is together. It's the biggest in the font, and that's how word cloud works. The size of the word corresponds to its frequency. So the more frequently a word occurs in the text, the larger its font size is going to be in the word cloud output. So this tells us that together, fun, well are some of the top words from the word cloud. How do you go about interpreting that? So I'll switch over to the slide deck. And what we learn from this is some vague sense that it seems like um, teams are working together well, potentially having fun. And that's about it. I want to keep this aside now, and we will come back to this at the very end when we look at the topic modeling output, and we'll compare those topic modeling outputs with the output of the word cloud.
We got a question. Let me jump in. Are
Yeah.
you removing the punctuation for tokenization and processing speed?
That's a good question. So punctuations are typically not considered to be meaningful when it comes to machine learning techniques of making sense out of text. All of the machine learning techniques that try to make sense out of text will eliminate punctuations either on their own, or if you read the documentation of those algorithms, they will explicitly ask you to eliminate the punctuations before you feed data into those algorithms. If you don't, it can either slow down your processing in the best of the scenario, and in the worst case scenario, you might get completely meaningless and useless outputs. Punctuations are not considered to be meaningful in the context of machine learning as it applies to text analytics. Any follow-ups?
No, that looks like it. Thanks.
All right, thank you. Okay, so the next step is one of the data preprocessing steps we talked about. That's tokenization and stop words. So, what exactly is tokenization? It's the process where you split up the body of text into smaller units called tokens so that you can apply the natural language processing techniques on top of it. Your tokens can be a single word, or it could be a phrase, just a collection of words. Or you could even break down a word into a group of characters and call that a token. What exactly do you call a token completely depends on the use case at hand. We also talked about stop word elimination. So stop words are those words which don't add any value to the sentence and can be totally ignored without compromising the meaning of the sentence. It's important to filter stop words before you do further processing. How do you filter stop words? How do you know which words are stop words? Uh, Thankfully, uh, the smart people who build these models have also taken care of this problem for us. Most of the popular natural language processing packages will come with a built-in list of stop words for most languages. So common languages like English, Spanish, French, and a bunch of languages will already have a predefined list of stop words coded into packages like Jensen, which we are going to use here. Most of these popular packages will also allow for customization or extension of the stop list. For example, in my company, um, when folks are answering the survey, what do you think about the health of your team? People will probably use the word uh, team very, very often. It's potentially a custom stop word that you should add to your pre-processing, because when people are answering the question, they're repeating some words from the question and it's not necessarily adding meaning to your processing. It might actually confuse the algorithm and show up as the most frequent word without really being meaningful. So, bottom line, packages will allow you to customize or extend the stop list as well. And depending on your use case, you might find that extremely valuable. So let's go back to the code and perform some of these steps. So going back to the Jupyter notebook, here's the code for converting the data frame to a list and then tokenizing those words. And then we are going to build the bigram and trigram models. So bigram and trigrams are cases where two words together make more sense than looking at those words individually. So let's run this cell and it's going to do the steps we talked about, which is tokenization and building bigrams and trigram models. You'll notice here there are a couple of instances where two words are separated by an underscore. Pretty good. So this is an example of the model having identified a bigram. Another example is lack of. This is also where the model has identified a bigram. The next thing we'll do is take care of the stop words and then the n-grams. We did not cover lemmatization yet. So before I run this cell, let me go back to the slide deck and we'll talk about lemmatization real quick. Okay, so n-grams and lemmatizations. What is an n-gram? We talked about the fact that there are bigrams where two words together make more sense than looking at those words individually. Trigrams is where three words together make sense rather than looking at those three words individually. And I should correct this in my slide deck. Sorry, I'm doing a few real-time corrections on my slide deck. We looked at a couple of examples of bigrams in our text as well. Lemmatization is the process of converting words to their roots. It uses contextual vocabulary and morphological analysis. Sounds super fancy. What it really means is it looks at the word or a collection of words before your target word as well as after your target word to try to understand what does your word mean in the context of the sentence. And then morphological analysis basically means how does the word change? How does it morph? So an example would be walking, walks, and walk. So walk is the lemma, the root of the word walking or walks. Morphology in this case means that the word walk has morphed, has transformed into its present progressive tense, walking. Sounds good so far? So I'll jump into the code that takes care of bigrams and lemmatizations. So we are defining the functions for removing the stop word over here. We are defining the function to use the bigram model that we created previously. We are defining the function to use the trigram model that we created previously. And then I'm defining the function to perform lemmatization. Okay, so let's define all of those functions real quick, and that's done. And the next thing we are going to do is invoke the functions we talked about to actually perform the process of removing the stop words, identifying the bigrams, and then lemmatizing the data. And then we'll look at what does the lemmatized data frame look like. All right, so this step might take a few seconds and it's done. So the lemmatized data frame looks like this. Nothing terribly interesting or meaningful to interpret from it, but just the good point to kind of know what your data looks like in the intermittent processing steps. All right, the next steps are creation of a dictionary and creation of a corpus. So let's go back to the slide deck real quick and talk about dictionary and corpus and then look at the demo to create them. So the reason we create a dictionary is because the LDA topic modeling algorithm needs a dictionary as an input. And then it also needs a corpus as an input. So what is a dictionary? You remember the lemmatization step that we did earlier? A dictionary is basically just the collection of the lemmatized words. And it comes with a unique ID that is assigned to each and every word. Remember how we talked about the fact that machine learning models don't like to work with text. They work much better with numbers. So this is a way where we can use numbers to tie the words and feed that number into the machine learning model. The corpus is next, and corpus is basically Latin for body. It refers to a collection of text. What we are doing here is creating a term document frequency corpus. So from the lemmatized words that we created in the dictionary, we are now trying to identify how many times did this word occur in each and every document. And we are going to create that data set. And we will use the unique ID from the dictionary as we build that data set. So let's jump into the demo and do the things that we talked about. So create a dictionary. Super simple. There is a method called corpora.dictionary, and you simply pass that method your lemmatized data frame. Just one line of code. That's literally it. Then you are creating a corpus of the term document frequency, where your corpus uh, or the code for creating that document frequency corpus is again just one line. There is a method called talk to bow, and you simply pass it your text data text corpus. And then this line will help us view the corpus in a human readable format. So let's run this cell and see what all of that looks like. All right, so this is the output. What this output is telling me is the term processes or process, the lemmatized term process, occurred only once in your entire dataset. The lemmatized term product occurred twice in your dataset. Scope, vision, these terms have occurred 2 times in your dataset. This is only a section of the output. If you look at more and more of these output rows, you will be able to see a lot more details. But we are only going to take a look at this section. Now that all of this is done, comes the fun part of building an LDA model. So a quick pause here before we jump into building the LDA model. If there are any questions about the content we covered so far.
No additional questions. If you do have questions, just please type them in the chat.
And I'm open to feedback. If I'm going too fast, feel free to ask me to slow down. If it's boring and putting folks to sleep, feel free to call that out as well, and I'll be happy to add some fun examples and add some context, some relevancy to some of these materials as well. It's the first time that I'm delivering this session, so any feedback is greatly appreciated.
So Timothy says it's great coverage and information so far, exclamation mark. And I think it's fine. It's we've got like another half hour for the regular meetings. I just didn't know with
Okay. Yeah, we should definitely be able to wrap up in the next half hour for sure. We are coming towards the steps of building the model, and then the next part is simply interpreting the output of the model.
And one more question. We missed the moment of the stop words, but did you mention that some models have built-in stop words, but we can also create custom stop words?
Yes, that is a good question. So I'll quickly go back to slide number 12 about stop words. Almost all of the natural language processing packages will have a built-in list of stop words for the language at hand. Stop words are language specific. The list of stop words for English is obviously different from the list of stop words for Spanish versus French. And almost all of the packages that I have looked at so far will also allow you to customize or extend that stop word list. Right? Anything else before we jump into building the model?
No, that's the last.
Perfect. Okay. So I will move this slide back to full screen. Okay. So what are we going to do to build the model? We'll use the Gensim library module called gensim.models.lda model. And this is what I mean. The code to actually build a model is ridiculously simple. It's literally just one line of code. all of the work that we did so far is the lion's share of the work that goes into building a model. So the key inputs to the model are going to be the corpus and the dictionary that we created so far. Everyone remembers what the corpus is and what the dictionary is, right? There will be a quiz after this session. Uh, and then the other parameter that you have to feed into the model is called num topics. It's basically the number of topics that you would like the model to identify. You're not telling the model what the topics are. You're simply asking the model from this body of text, shake it all around and try to identify 2 topics for me or 3 topics for me. And this is the iterative phase. This is where you have to iterate from 2 to n and look at the output each and every time. The output is going to be the topic ID, the keywords for each and every topic, and something called the importance score for each and every keyword. So let's jump into the exciting part of building the model. So all of this is one line of code. You're building the model with just one line of code. This is the corpus that you pass in as the input. This is the frequency, the term frequency document that you pass in as the input. And here is the num topics parameter that you also pass in as the input. The remaining input variables are pretty standard. You don't need to change the defaults. Just leave the defaults be. And then we have a line of code to print the output. The output, which is basically the term and the importance score associated with every term. So let's quickly run this cell to build the model. And it's done. So the model has identified 2 topics, topic number 0 and topic number 1. For topic number 0, it has identified these terms: team, good, improvement, overall, feel, need, so on and so forth. And for every term, it has associated an importance score with that term. So how important is that word within the topic? Then for topic 1, you can go through a similar output. Here are all the words that the model has identified that belong to topic number 1, the next topic, and then the importance score associated with each and every word. The importance score ranges from 0 minimum to 1 maximum. Then there are a couple of other metrics which are much better to help figure out what's going on with your model than just the importance score, which is at the word level. You want to understand how your model is behaving at the topic level, and for understanding that, we use 2 key performance indicators: perplexity and coherence. So I'll switch back to the slide deck and we'll quickly talk about what are these model performance metrics. So perplexity is a metrics that measures how surprised your model is when it comes across a brand new data set. Think of it like training and testing your model, which means when you train your model, you show it some data and the model has made certain assumptions. The model has learned something from the training data set that you showed it. Now you show the model the testing data set, which the model has never seen before. If the model is surprised by the new data, that means your model is perplexed. The model couldn't figure out what does the new data mean from the things that it learned previously. So the higher the perplexity score, the worse it is. The lower the value of perplexity score, the better it is. Then you also want to look at topic coherence. Uh, the word coherence here means pretty much the same that it means in the English language. A set of facts, a set of statements are supposed to be coherent if they support each other. So when you apply that to topic modeling, what you're looking for is similarity in the different words within the same topic. When the similarity between the different words of the same topic is high, then that topic is supposed to be coherent. The score for such a model, the coherence score for such a model will be high, and the higher the value of your coherence score, the better it is. Oops. So we'll take a quick look at the coherence scores and the perplexity scores of these two models. Let's run this, and it's going to take a second to calculate coherence. There we go. Okay, so the perplexity score is -6 and the coherence score is 0.2. In its absolute sense, what do these numbers mean? Are they good? Are they bad? We don't know. The only way to tell if these numbers are good or bad is when you look at these numbers again after iterating through the model. So we have run the model for 2 topics. We are going to run the model for 3 topics and look at the same numbers. We're going to then run the model for 4 topics and look at these same numbers. If the perplexity score increases, that's bad. That means the model has gone worse. If the perplexity score decreases, then the model is improving. Same with the coherence score. The coherence score, when you are training the model for 2 topics versus 3 topics versus 4 topics, we'll look at how the score moves. If it moves higher, it means the model is improving. If it goes lower, that means the model is getting worse. Then the next thing we'll look at is the visualization. And I'm going to quickly talk about the intertopic distance map when it comes to visualizing. So optimizing for perplexity and coherence, as we talked about, may not always lead to topics that make sense to us as humans. Uh, they might result in a model that is mathematically or statistically amazing, uh, but has very little value in terms of human interpretable topics. So we do want to look at something that we as humans can make sense out of. That's where the intertopic distance map comes into picture. We use a package called PyLDAvis. Sorry for the spelling mistake here. It's PyLDAvis package, and it creates an interactive web-based visualization. It has some bubbles and it has a bar chart. Each bubble represents a topic, and when you click on the bubble, it's going to bring up the bar chart for the bubble, where every bar represents the word within that topic. So let's build that for the model we just created and take a look at it. So this cell is going to build the intertopic distance map and show it right here for our convenience. All right, it's done. The intertopic distance map is ready. We had set num topics to 2 over here. So it's showing me 2 bubbles because we asked the model to create 2 topics. When I click on bubble 1, I look at the right hand side. It's telling me that bubble 1, so topic 1, represents 58.2% of the tokens. So topic 1 represents just over half of all of the information found by the model. And then it's telling me the various words that it found in the topic. So team, work, good, great, feel, support. These are all the different words that it found in the topic. And how many times did the word occur in that topic? It's trying to tell me that as well. If I click on the second bubble, you will notice that it's telling me topic 2 is now about 41.8% of the total tokens, and is telling me the top 30 words for topic 2. You'll notice here how team, which was about 200 for topic 1, has now changed to about 50 for topic 2. The word good, which was just over 50 in topic 1, has gone to maybe about 40-ish in topic 2. So it's now trying to create the distribution of topics that we had previously talked about, and then the topic is a cluster of words. Every topic is a cluster of words, and this output is trying to show us these distribution of topics and the words and how they are clustered and distributed across the topics in a way that we as humans can understand. All right, so that's how it all looks like for number of topics equal to 2 as input. What we are going to do next is run all of this again and again uh, for 3 topics and 4 topics and see what everything looks like. Okay, so we'll retrain the LDA model. The only thing I have changed is num topics is equal to 3. So let's run this and see what happens. We have the perplexity score down here, and we have the coherence score. Notice how the coherence score has improved. And this is what the chart looks like. There are 3 bubbles. They're nicely separated. And for every bubble, we can look at the words. We'll actually look at it deeper in just a minute. But I want to now do the exact same thing by changing num topics to 4. So let's run this guy and see what our numbers look like. So the perplexity score has come back, coherence score has come back. I believe the coherence score may have increased or may have improved slightly. Yeah, it went from 0.24 to 0.27. Perplexity score also increased, which is not necessarily great. So let's look at the intertopic distance map. And here you'll notice there is a situation where 2 bubbles have overlap. What does this really mean? So this is where we are going to go into the human interpretation. What this means is we have overshot the training of the model. Uh, the ideal state of the intertopic distance map is that the bubbles that you see on the left hand side, which represent topics, those bubbles should not overlap. They should not even touch each other. Ideally, those bubbles should be as far apart as possible on this chart. That represents a healthy identification of the right number of topics. So, just by looking at this intertopic distance map, I can tell that there are 3 topics, which is the ideal number of topics in this body of text. For your convenience, I have collated all of this into a table previously, so we don't have to compare any of this in real time. When you have 2 topics, this is the model perplexity score and then the topic coherence score. And the bubbles are far apart. They are well spaced across the chart. So we know that this body of text has at least 2 good topics. Then when it comes to 3 topics, the model perplexity score increased, which is not necessarily good, but the topic coherence score also increased, which is great. And then the intertopic distance map. So this is the intertopic distance map for 3 topics. It looks great. The 3 bubbles are as far apart as they possibly can be. Then we look at 4 topics. The perplexity score has gotten even worse. The topic coherence score has gotten better, but does that really translate into human readable topics? And that's what the intertopic distance map is telling us, that two of the four bubbles have overlapped, which means that if you're asking the model to identify four topics, two of those topics have a significant crossover. It has a significant overlap. So topic 1 and 2 are actually not two separate topics. They're just one single topic. So 3 is the ideal number of topics in this situation. Next up is inferring the labels from those topics. And I'll take a quick pause over here to see if there are any questions about the material we covered so far.
Just got one additional question. What are some of the hyperparameter tunings we'll most likely see for LDA? Can you explain why perplexity is negative and it is being more negative is bad?
Yep. So there are several questions here. One is about the hyperparameter tuning. So in the topic modeling input, you will see all of these other variables that we did not change. These are some of the parameters that you could potentially tune. Hyperparameter tuning works really well when you have a model that spits out a numerical output. In case of text analytics, I have tried, and trust me, I have really tried and found very, very little value um, for the efforts you would put in for hyperparameter tuning. It might be different uh, with different data sets. Typically, it is true across the board for the most part that text models don't really respond well to hyperparameter tuning, especially the LDA kind. Now, if you are going into neural networks, you might find hyperparameter tuning is useful, uh, which is one of the talks that I want to take up in the future about how to do all of this using neural networks. But we'll cross that bridge when we get there. So that was one of the questions. Can you remind me of this next question again, Julie?
Sure. Can you explain why perplexity is negative and it being more negative is bad?
Yes. All right. So the perplexity as a measure, uh, I believe the range goes from -100 to +100. That's just the nature of the metric. You and I have no control over the fact that the output of the model for perplexity, its range is from -100 to +100. A perplexity being more negative, you know what? I think um, I you are 100% right with the question because I misspoke. When the perplexity score is more negative, that means it's lower. And what that means is your model is improving, because we talked about the fact that the lower the perplexity, the better is your model. The higher the perplexity, the worse is your model. So my apologies for misspeaking earlier. I stand corrected. As the perplexity score becomes more and more negative, it means that the perplexity score is becoming lower and lower as you are increasing the number of topics. What that means is your model is getting better. So both of these metrics, perplexity and topic coherence, are moving in the right direction as far as numerical analysis of the metrics are concerned. Thanks for calling that out.
And that's a for the questions. He just said, thank you for explaining. He's new to this realm of machine learning, so your insights are invaluable.
And I should be the one thanking you for calling that out, because I totally had a uh, brain fart there, and I said that the perplexity score is getting worse when in fact it was actually getting better. So thanks for keeping me honest there. All right, then the next thing we do is we have identified that 3 topics is the ideal number of topics in this case, because the perplexity scores are getting better between 2 topics to 3 topics. But if you go from 3 topics to 4 topics, while the metrics are getting better, the chart doesn't make any sense. The chart is telling us that at 4 topics, you're basically getting an overlapping of the 2 topics. So there isn't any sense in going any further. In fact, the right thing to do is take a step back. And 3 topics is the ideal number of topics. So we'll look at the chart for 3 topics, and we are going to click on each and every one of these topics. And I will rerun this because it might help fit much better on the screen. Come on. All right. No, it's not fitting any better on the screen. Sorry about that. And this is probably why I took a screenshot. So when you click on topic 1, it's telling you topic 1 is about 43% weightage in the body of text, and you get to see the top n number of words for topic 1. You do the same thing for topic 2 and topic 3. And the slide over here is where I have collected the top 10 terms. And this is where your human common sense as well as your subject matter knowledge about the data that you're analyzing comes into picture. So looking at these terms and knowing the fact that this is coming from a team health survey, what I can interpret is that topic 1 tells me that the overall team health feels good, is positive, and is green. Green is one of the traffic light indicators that people use to talk about their team's health. Green is great, yellow is neutral, and red is bad. So some of the business knowledge, some of the subject matter knowledge is helpful in inferring the labels for these topics. Topic number 2, looking at the top 10 words in topic number 2, I can tell that a good label for it would be that people like their work, the work is great, they have good support, and they seem to have a lot of fun while working. And then the last topic, topic number 3, when I look at all the terms and I put together my human common sense with the subject matter knowledge, the topic that I can infer from it is that while everything is good from topic 1 and topic 2, there is still some room for improvement. People feel that we could do better. We are good, but we could do better. So those are the 3 topics that you can infer from the intertopic chart and the distribution of the words of the intertopic chart. So once we have done with this interpretation, let's go back to the word cloud that we created a while ago and then compare the analysis, the inferences that we were able to draw from the word cloud versus the inference that we are able to draw from topic modeling. The word cloud, it simply indicates that together is the most frequently occurring keyword, and it's followed by work, fun, well, and team. So all of these words have positive connotations You could potentially say that you can interpret that the teams are working well together over here. That's about it. You don't really get any deeper insights. Now, let's compare that with the outputs of the topic modeling algorithm. You are able to get three topics. The first topic is telling us that the overall team health is good, it's positive. And we are also able to say that about 43% of the text has this topic. The next topic we are able to identify is that people are having fun at work. The work is great and the teams are supportive. Uh, and we are able to tell that this topic is found in about 37% of all the responses. Lastly, the topic, there is some room for improvement. So, in spite of the fact that things are going great, health is good, everyone is supportive, there's great work, there seems to be some room for improvement. And the fact that there is some room for improvement has been expressed in about 20% of all the responses. So, when you combine all of these uh, outputs with your business context or subject matter expertise, your knowledge about the organization, I can give a summary readout to my business stakeholder, which in this case is the VP of IT, that the prevalent consensus amongst all the survey respondents is that the overall team health is good, it's positive. Just under half of the survey respondents feel this way. The next thing I can tell my VP of IT is that over a third of the survey respondents indicate that the teams are supportive of their team members. They're having a lot of fun at work and the work is great. So it's a very positive team environment. Um, so the VP of IT knows that they're doing something right for the teams to feel this way. And then the last insight I can share with my VP of IT is that about a fifth, so about 20% of the survey responses do indicate that while things are mostly positive, there are some areas for improvement. What exactly those areas for improvement might be, um, people don't really have clarity on that. People haven't really told us what exactly it is that they would like to be improved. Uh, but they are telling us that there is some room for improvement. So, this is where the managers of those respective teams might want to have conversations with their team about identifying any issues that their teams might be facing and potentially addressing those issues. I'll take a quick pause. Any questions so far?
No additional questions.
All right. Then the last couple of things I'm going to cover is the automation. So we talked about the fact that we iterate through the number of topics. In this case, it was really easy because we only iterated three times, 2, 3, and 4, before we discovered that 4 is no good. 3 is the ideal number of topics. You may come across a situation where you need a lot more iterations. You could potentially write a loop to perform those iterations. That's one idea for automation. There is a package called LDA Mallet model. It's an open source package that will perform these iterations for you. It will write a for loop for you, and you don't necessarily have to go about doing this part. Uh, Gensim provides a wrapper to facilitate LDM mallets, intertopic distance estimation, as well as the inferences of topic distribution. It's a little bit more involved to implement these automation techniques, and actually doing this is out of the scope of today's discussion. So on that note, we come to wrapping up today's conversation. Uh, we introduced the NLP technique of topic modeling. We looked at Anaconda Jupyter Notebook as the demo environment for performing topic modeling. We looked at the data cleaning and preparation steps. We walked through the iterative process of training the topic models and identifying the optimal solution. We also looked at how to interpret the output of a topic modeling algorithm. And then we got to compare the benefits of these deeper insights in contrast with some of the shallower techniques like word cloud. And lastly, we also talked about how you could potentially take these topic modeling machine learning outputs and then apply your human common sense, apply your subject matter and organization knowledge, and give meaningful insights to your business stakeholders, which in the case of this example was an IT executive. That's pretty much it. That's a wrap for today. I would like to thank everyone for dialing in and listening and for all of your interesting questions. And a big thanks to Julie and Gary for giving me the opportunity to present this topic for the very first time on my home turf of St. Louis.
That sounds great. Does anybody else have any questions? Timothy, thank you so much for the questions that you've been asking in the chat. They really add a lot to the presentation for everybody. Very helpful. So I'm not seeing any additional questions.